You now have an idea on how to design an instrument that can measure current and voltage. This time, let's try to design an instrument that can measure electromotive force, or basically it's the same as potential difference. So I'm talking about potentiometer. A potentiometer is an instrument that is used for measuring or regulating EMF or electromotive force. Its operation is based on the concept of variable resistance, which we will now discuss. For the basic design of potentiometer, you must have an EMF source. Let's name this as V sub 1. And a variable resistor that regulates current. So let's put an arrow sign here to denote that this is a variable resistor. Let's name this as R sub 1. And it is connected through a resistance wire. So let me change the color of this resistance wire. So resistance wire is important because we assume that this wire has a uniform resistance. So because of this EMF source, current flows this way. And the amount of current can be regulated by this variable resistance. So we place a meter stick beside this resistance wire. Here we attach a zero-center galvanometer. When we say zero-center galvanometer, its needle points to zero, and this zero level is at the middle part of the scale of the galvanometer. So it can deflect this way or this way depending on the direction of the current. So this galvanometer is attached to a sliding conductor. So let me emphasize that this portion can be varied. So I can move this contact here or here. So the important thing is this contact is movable with respect to our resistance wire. So let's label this point as X and this end of the resistance wire as Y. The other end of the galvanometer is actually connected to a switch. So this is the switch. It can be connected in this conductor or in this conductor. This connection is used for calibrating the potentiometer, and the other one is the actual connection used for measuring an unknown voltage. So this connection here, if you try to connect this galvanometer here, is used for the actual measurement of an unknown voltage. Let's name this unknown voltage as V sub X. So obviously, since this is the end part of this EMF source, this is basically the negative terminal of the potentiometer, and since essentially this is the part that is connected to the positive terminal of the primary EMF source of the potentiometer, so this is the positive terminal. Now let's return to this connection for calibrating the potentiometer. So before we could actually measure an unknown voltage, in other words, before we can connect this terminal to a specific component or part of an external circuit where we want to measure the voltage or the EMF, we should calibrate the entire potentiometer. So in order to do that, we connect the switch in such a way it is connected through this resistor and an EMF source. Let's name this EMF source as the calibration EMF source and this one as the calibration resistor. To calibrate the potentiometer using this known voltage of V sub cal or calibration voltage, randomly choose a point between X and Y. So let's name this point as Z. Of course, at your first attempt, there will be a deflection in the galvanometer. Once you connect this switch to this EMF used for calibration, there will be a deflection in this needle because of this calibration EMF and this one. Let's say this galvanometer is deflected in this way. So to return this galvanometer to zero value, we should adjust this variable resistor in such a way the galvanometer will return to its zero reading. After some adjustments, when your galvanometer reaches the zero reading again, then this means that this voltage from point X to point Z is equal to the voltage of VCAL, because when you have a zero reading in the galvanometer, that means this voltage here is equal to the voltage of the calibration EMF. Hence, I can write this as the potential here is V sub XZ because it's from this point X up to this point Z is equal to the calibration voltage. Now, when this galvanometer is touching point Z, on this resistance wire, we could actually calculate a specific voltage per unit length. So the voltage in this region is V sub xz, and its length can be read in this meter stick or ruler. So for now, let's represent this length as L sub cal, or calibration length, and this is the length from point X to point Z. So the voltage per unit length in this region is V sub xz divided by L sub cal, or the calibration length. And based on this expression, this is also equal to the calibration voltage divided by L sub cal. Once we have this value, the voltage per unit length, we could now disconnect this switch and then transfer the connection to this part of the circuit. So we can now use these terminals to measure an unknown voltage of a specific component or portion of an external circuit. So once this switch is connected to this, let's say V sub x, the galvanometer will now be deflected. Let's say it's deflected here. Let's assume that we connect this to an unknown circuit or component. This can be a battery or a sophisticated circuit or an electronic component and so on. So once we connect this with a device, we can measure its potential difference or EMF. And once we connect it, apparently the galvanometer will be deflected. And this time, we can now adjust this sliding contact in such a way the galvanometer will return to its zero reading. So you could move this to the right, or you could move this to the left. And once the galvanometer returns to its zero reading, then you can stop adjusting this sliding contact, and then you'll now have a new length. Let us represent the new length as L sub x. So again, this is the new length. So the value of V sub x is now easy to calculate, and we can measure it based on the length of the resistance wire that results to a zero reading in the galvanometer, and this is equal to L sub x multiplied to the voltage per unit length. So this is the basic operation behind a potentiometer. Let's now discuss an instrument that can be used to measure resistance. You already have an idea on how to design an instrument that can measure current, and then an instrument that can measure voltage. This time, let's talk about an instrument that can measure resistance. So for example, you have an unknown resistance R sub x. So if you have a voltmeter and an ammeter, then all you need to have is an external EMF source, for example this one, and then try to connect this to our resistor with unknown resistance. And in order to calculate its resistance, if you have an ammeter, you connect it in series. And then if you have a voltmeter, you connect it in parallel with our resistor. So once we measure the voltage across the resistor and the current through the resistor, then we could actually use Ohm's law to calculate for the resistance of this unknown resistor. However, recall that in the design of ammeter and voltmeter, an ammeter requires a shunt resistor while a voltmeter requires a multiplier resistor. So in the process, this ammeter and voltmeter can somehow introduce some errors because they can introduce potential drops in measuring the original resistance of the resistor. In connection to that, we explore another instrument, the Wheatstone Bridge design of an instrument that can measure resistance. So to begin with, imagine we have an external EMF source. Let's represent this with E, epsilon. And then it's connected to a network of resistors. So this network of resistor is commonly known as a Wheatstone bridge. So let's name this resistor as R sub 1 and this one as R sub 2. So here, instead of naming this as R sub 3, I'll just name this as R sub x, because this is where we will position our resistor with an unknown resistance. And this is R sub 4. Actually, in a Wheatstone bridge design, you could actually position R sub x in the position of R sub 1 or R sub 2 or R sub 4. It doesn't really matter because I'll teach you how to derive the expression for R sub x given R sub 1, R sub 2, and R sub 4. Now, in the middle of this network of resistors is a galvanometer connected between R sub 1 and R sub x and R sub 2 and R sub 4. Now, this is our setup for measuring an unknown resistance of a resistor given R sub 1, R sub 2, and R sub 4. Now, in this setup, we assume that R sub 4 is a variable resistor. But actually, it doesn't really matter if R sub 1 is the variable resistor or R sub 2 and so on. The important thing is it must contain at least one variable resistor so that we could actually force the reading in the galvanometer to be zero, because apparently once we connect an EMF source and current flows this way, then there's a huge chance that current will flow through the galvanometer, especially if all these four resistors do not have equal resistances. So to simplify calculations, we will vary the value of the variable resistor in such a way there will be a zero reading in the galvanometer. So again, once we connect the EMF source through this network of resistor and the galvanometer deflects, for example, this is the scale of the galvanometer and it has a zero center scale. So once we connect the EMF and the galvanometer deflects this way, we adjust the value of R sub 4 or the variable resistor in such a way the galvanometer returns to zero reading. Once we achieve that, we record the values of R sub 1, R sub 2, and R sub 4. Again, in this circuit, we assume that R sub 4 is the variable resistor while R sub 1 and R sub 2 have fixed values of resistances. So our goal is to calculate the resistance of this unknown resistor. We have a junction here. Some of the current flows in this path and some of the current flows in this path. When the galvanometer reaches a zero reading, we are sure that the voltage drop in R sub 1 and the voltage drop in R sub 2 must be equal. Otherwise, if they are not equal, some of the charges will be pushed through the galvanometer and flow in this direction or this direction. So in other words, if a galvanometer has a zero reading, then the voltage drop in R sub 1 and the voltage drop in R sub 2 must be equal. And the same goes for the voltage drop in R sub x and R sub 4. And since this path is just a single path, we could just represent the current passing through R sub 1 and R sub x with I sub 1, and the current that passes through R sub 2 and R sub 4 as I sub 2. So deriving the formula for R sub x in terms of R sub 1, R sub 2, and R sub 4, we write down our basic assumption that in order for the galvanometer to have zero reading, the potential drops across R sub 1 and R sub 2 must be equal. V sub 1 equals V sub 2. So using Ohm's law, this is equal to I sub 1 times R sub 1 equals I sub 2 R sub 2. Similarly, the potential drop across R sub x and the potential drop across R sub 4 must be equal. Using Ohm's law, this is equal to I sub 1 times R sub x equals I sub 2 R sub 4. So rearranging this, I'll have I sub 1 over I sub 2 equals R sub 2 over R sub 1. And here, I'll rearrange this in terms of I sub 1 over I sub 2 equals R sub 4 over R sub x. Since I sub 1 divided by I sub 2 appear in both sides, I can equate these two. So I'll have R sub 2 divided by R sub 1 equals R sub 4 divided by R sub x. Therefore, the unknown resistance is equal to R1 over R2 times the value of the variable resistor. So given this setup, you could actually measure the resistance of a component without using external voltmeter or external ammeter. All you need to have are resistors with known values of resistances and a variable resistor plus a galvanometer. So let's have an example. Determine the value of the unknown resistance R sub x. So here we transfer the location of the resistor with unknown resistance relative to the other resistors. Determine the value of the unknown resistance R sub x in the circuit shown below. Assume that the galvanometer has a null reading. So the value of R sub 1 is 12,000 ohms, R sub 3 is 32,000 ohms, R sub 4 is 40,000 ohms, and we wish to find the value of R sub x. So since the galvanometer has a zero reading, the voltage drops across R sub 1 and R sub x must be equal. Also, the voltage drops across R sub 3 and R sub 4 must be equal. Let's assume that since we have a junction here, if this EMF source drives the current in this direction, so this current will be divided in this path. Let's name this current as I sub 1 and let's name this current as I sub 2. So going back to our expressions, this is equal to I sub 1 R sub 1 equals I sub 2 R sub x, and B sub 3 is I sub 1 R sub 3 equals I sub 2 R sub 4. I'll rewrite this as I sub 1 over I sub 2 equals R sub x over R sub 1. And this one I'll write as I sub 1 over I sub 2 equals R sub 4 over R sub 3. Since these terms are the same, we can equate these terms. So Rx over R1 equals R4 over R3. Therefore, Rx equals R4 over R3 times R sub 1. So plugging in these numerical values, R sub x is then equal to 15,000 ohms. For your laboratory experiment, so you will be using 422k ohm resistors. If you're using a simulation, you could actually somewhat vary their resistances. It's up to you to vary the resistances. For example, R sub 1 can be equal to 2,250 ohms. R sub 2 can be equal to 2,220 ohms. R sub 3 can be equal to 2,160 ohms. R sub 4 can be equal to 2,200 ohms, and so on, as long as they are approximately equal to 22k ohms. So our goal here is to create a bridge circuit. Initially, since all the resistors do not have equal values, apparently the galvanometer will have a deflection. And since we have an unbalanced bridge type circuit, we will be utilizing Thevenin equivalent circuit and derive the current and the internal resistance of the galvanometer. So in this experiment, since we are now familiar with the calculations when we have a bridge type circuit that consists of two resistors with fixed resistances and a resistor with unknown resistance and a variable resistor, we will explore a bridge type circuit wherein the values of the four resistors are fixed and we would like to calculate the internal resistance and the current passing through a galvanometer. Once you have these resistors, arrange them in a bridge circuit like this. So once you arrange the resistors into this bridge circuit, try to supply it or apply a 5-volt EMF source across this network of resistors. So obviously, since all the resistors here are not perfectly equal, remember that we intentionally introduce some variations in their resistances, then there will be a current flowing through the galvanometer. So to calculate the current and the internal resistance of the galvanometer, we will convert this circuit into a simple series circuit like this using Thevenin theorem. So when you apply Thevenin theorem, your circuit can be simplified into a circuit with one EMF source, let's call this the Thevenin voltage, and one resistor, let's call this the Thevenin resistor. And based on this, once we have a value for the Thevenin resistance and the Thevenin voltage, it is easy to calculate the current that passes through this because when you have a series connection, only one type of current passes through the components. And if we assume that if we represent the current that passes through the galvanometer as I sub G, then I sub G is simply equal to the Thevenin voltage divided by the Thevenin resistance. And once we have this value of current, if we try to use Kirchhoff's loop rule, if we have a Thevenin voltage source, and there will be a voltage drop in this region, and then another voltage drop in this region. And let's represent the internal resistance of the galvanometer as R sub G. Since we have a value for the Thevenin voltage, the Thevenin resistance, and the current, sorry, this is I sub G, we could actually calculate for the internal resistance of the galvanometer. So to apply Thevenin's theorem, let me draw this circuit wherein this diamond-shaped network of resistors is represented by a simpler one. So this is my EMF, and they are connected through R sub 1, R sub 2, R sub 3, and R sub 4. So I have a galvanometer here. To find the Thevenin voltage across the galvanometer, so essentially, if we return to this figure, we will assume that the galvanometer is connected to a circuit in such a way its resistance is represented by a Thevenin resistance and its voltage is represented by a Thevenin voltage. From the point of view of the galvanometer, I'd like to calculate the Thevenin voltage, and if you try to look at this figure, I could just remove this galvanometer and then calculate the voltage from this point A to this point B. So here, I could just actually imagine that this is point A and then this is point B. To calculate the equivalent voltage or the Thevenin voltage, notice that this part of the EMF source, practically speaking, this is connected to the ground. And since this is connected to the ground, this portion is also connected to the ground. I could actually redraw this as this is my EMF. This is connected to the ground. And this is connected to the ground. So obviously, this looks familiar. We now have a voltage divider, and it is being supplied with a voltage E coming from this EMF source. Let's look at the voltage across our source. If we try to measure its voltage, it's actually measured from the positive terminal and to the negative terminal, and this negative terminal is connected to the ground. So here, if we want to measure the potential at point A, then we will be measuring the potential at this point with respect to the ground. And to calculate the potential at point A, and by the way, this is point B, we use the equation for voltage divider. So here, the voltage at point A is equal to the source E, I'll put it here, times the factor given by this voltage divider. Remember that this is R sub 1, R sub 3, R sub 2, R sub 4. So using the concept of voltage divider, the voltage at point A is equal to R sub 3 over R sub 1 plus R sub 3. And the voltage at point B, which is this point, is equal to the voltage at this point with respect to the ground. And since this is being supplied by this voltage, we will multiply this with the factor given by this voltage divider, which is R sub 4 over R sub 2 plus R sub 4. Therefore, the potential difference between points A and B, which, by the way, this is also our Thevenin voltage, is equal to V sub A minus V sub B. Plugging this expression here, the Thevenin equivalent voltage is then equal to R sub 3 over R sub 1 plus R sub 3 minus R sub 4 and over R sub 2 plus R sub 4. Now, since both of them have a factor E, I'll factor out E. And this is our expression for the equivalent Thevenin voltage. So again, we now have a value for Thevenin voltage. Let's now look for the value for equivalent Thevenin resistance. So I will copy this figure. Now, when we calculate the equivalent Thevenin resistance, when we have an independent source like this EMF source, we replace it with a short circuit. In other words, I'll just replace this with a simple wire, a short circuit. So I'll just replace it with a wire. So from the point of view of points A and B, this looks like I'll try to transfer this connection outside and then this one to this side. Notice that this length of wire, I could just put this inside. So let me redraw this figure from the point of view of points A and B. Notice that at the middle part of R sub 1 and R sub 2, we have a piece of wire. And if this wire is connected to a point between R sub 3 and R sub 4, so it actually looks like this. However, notice that it is somewhat confusing to calculate the equivalent resistance of this network of resistors because they are not readily presented in such a way you can discern which resistors are in series connection with one another and which resistors are in parallel with the other resistor. So let's try to redraw this in such a way it is easier to calculate the equivalent resistance in parallel connection and the equivalent resistance in series connection. So starting from point A, we have R sub 1 and R sub 3. The current can flow this way or the current can flow this way. So it seems that if we will just represent this with a single wire between resistors R sub 1 and R sub 3, essentially it's the same as I'll try to represent it with this junction, because the possibilities are still the same. The combination of current flows remains the same. So this is R sub 2 and R sub 4. To help us visualize that this preserves the combination of current flows, the possible current flows in this circuit. So the current can flow from point A and then it can be divided in this junction into two. So a portion of the current can flow through R sub 2 and a portion of the current can flow through R sub 4. So notice that in this arrangement, it is still possible. So here, the current can actually flow through R sub 2 and R sub 4 at the same time. And the same goes if the current flow this way. Such current flow is still possible in this arrangement. So essentially, in terms of current flow, this circuit is equivalent to this circuit. And the only difference is that the equivalent resistance of this network is easier to calculate. So the resistance across A and B is also the Thevenin resistance, and this is equal to, the Thevenin resistance is equal to 1 over 1 R sub 1 plus 1 over R sub 3 plus 1 over 1 over R sub 2 plus 1 over R sub 4. So this is equivalent to R sub TH equals R sub 1 plus R sub 3 over R1 R3 plus 1 over R2 plus R4 over R2 R4, and this is equal to R1 R3 over R1 plus R3 plus. So once we have the values for equivalent Thevenin resistance and equivalent Thevenin voltage, it is now easy to calculate the current passing through the galvanometer and also the internal resistance of the galvanometer. So you'll now be able to calculate for I sub g and R sub g. And once you have these values, it is now easy to follow the succeeding steps in your laboratory experiment. Now, when it comes to other values like delta R sub i's, please follow the indicated formula in the procedure. So apparently, if you're using a simulation, please do not panic if you have exceedingly high or extremely low values for percent error. Note that this is a simulation, so please read the procedure carefully. If you have exceedingly high or extremely low percent error, don't panic, just try to figure it out why. Remember that you're using a simulation, so there are a lot of assumptions there, and that's it. Don't forget to like this video, subscribe to my YouTube channel, and hit the notification bell button for awesome updates. Thank you for watching!